Hi, this is Bono. Today, let's talk about a part that's incredibly handy in electronics, the operational amplifier, or op-amp. An op-amp can amplify a small signal up to a size that's easy to work with, so it shows up everywhere, in circuits that use microphones and sensors, and many more. The name sounds intimidating, but once you grasp a few simple rules, the way it works really does make sense. In this video, we'll go in order from what an op-amp actually is, all the way to its classic uses, the non-inverting amplifier, the inverting amplifier, the voltage follower, and the summing circuit. If op-amps have always felt a bit hard to you, please watch through to the end. First, let's nail down what an op-amp is. An op-amp has two inputs, a plus and a minus, and one output. The most important thing here is that an op-amp amplifies the difference in voltage between its two inputs. I used to think an op-amp was just a part that makes a voltage bigger, but in fact it responds to the difference between the two inputs. Keep in mind that it does not simply boost one of the inputs on its own. And that amplification factor is very large, roughly tens of thousands to a million times, though it varies by model. In other words, an op-amp will amplify even the tiniest difference by a huge amount. Note that an op-amp doesn't generate energy by itself, so it needs a power supply to operate. Now that we know what an op-amp does, let's look at why amplification is needed in the first place. In fact, the signals that the sensors and microphones around us put out are often very small. For example, the sound a microphone picks up is only a few millivolts as is, far too small to read with a microcontroller or to drive a speaker. That's where the op-amp comes in. Just like a microphone picks up a faint voice and makes it louder, the op-amp amplifies a weak electrical signal up to a size that's easy to handle. So where exactly are op-amps used? Let's look at a few familiar examples. The classic one is the microphone amplifier. It amplifies the small sound signal a microphone picks up to a usable size. Next is amplifying sensor signals. It boosts the tiny voltage from a temperature or light sensor so a microcontroller can read it. It's also used in mixes, which combine several sound signals into one. That's the job of the summing circuit we'll see later. And it's used in circuits that compare a signal against a reference voltage to decide which is larger. Like this, op-amps are at work inside all sorts of everyday gear as the part that handles signals. Next, let's take a rough look inside the op-amp with a block diagram. We won't get into the individual components. Thinking of it as 3 blocks is plenty. First, at the entrance is the differential input stage. This takes in the two inputs and extracts their difference. It's built so that almost no current flows into the inputs. Next is the amplifier stage, where the signal is amplified by a very large factor. And last is the output stage, which shapes the amplified signal so it can firmly drive external parts and sends it out. For now, just remember 2 features. Almost no current flows into the inputs, and it amplifies by a very large factor inside. These are important properties we'll use again and again. Here, there's one problem. A moment ago, I said an op-amp amplifies by tens of thousands of times. But used as is, even the tiniest difference slams the output all the way to its limit, which makes it useless as an amplifier. This is where the idea of feedback comes in. Feedback means returning part of the output back to the minus input. With this, if the output grows too large, a brake is automatically applied and it settles at a sensible gain. And by changing the value of the resistor used to feed it back, you can set the gain to whatever size you like. This feedback is the very key to using an op-amp well. Once you apply feedback, one very handy rule becomes available, the virtual short. The virtual short says that in the normal state, when feedback is working and the output isn't railed, the voltages at the plus input and the minus input become almost the same. This happens as a result of the op-amp adjusting its output to drive the difference between the two inputs towards zero. What I want you to be careful about is that the two inputs are not connected by a wire. The voltages simply end up matching as a result, and no current flows between the inputs either. That's why it's called a virtual short. Using these two rules, the two inputs are at nearly the same voltage and almost no current flows into the inputs. The gains of the amplifier circuits coming up become clear and simple. Now let's use the virtual short to look at our first amplifier circuit, the non-inverting amplifier. In this circuit, the signal you want to amplify goes into the plus input, and from the output, two resistors feed a voltage back to the minus input. By the virtual short rule, the voltage at the minus input becomes the same as the plus input, that is, the same as the input voltage. Then, since almost no current flows into the input, the same current flows through both feedback resistors. Using that relationship, we can work out how large the output becomes. As a result, the gain of this circuit is 1 plus Rf divided by Rin. Rf is the resistor that feeds back from the output, and Rin is the resistor from the minus input to ground. In this circuit, the input and the output have the same direction, and the gain is always 1 or more. But one caution, no matter how large you make the gain, the output can never exceed the supply voltage. Raising the resistor ratio does not amplify without limit. Keep in mind that it tops out within the range of the supply. Next is the inverting amplifier. This time the signal you want to amplify goes through a resistor into the minus input, and the plus input is connected to ground. Since the plus input is at ground, that is 0 volts, the virtual short rule makes the minus input nearly 0 volts too. This point, which appears to be at 0 volts, is called a virtual ground. Here too, since almost no current flows into the input, the current coming through the input resistor flows straight on into the output resistor. The gain is set by that relationship. As a result, the gain of this circuit is minus Rf divided by Rin. What I want you to watch out for is that this minus does not mean the voltage gets smaller. It means the input and output directions are flipped. The size itself is Rf divided by Rin, and depending on how you pick the resistors, it can be larger or smaller than 1. Next is a slightly unusual use, the voltage follower. This is a circuit that feeds the output straight back to the minus input, and the gain is exactly 1. A gain of 1 means the same voltage as the input simply comes out. You might wonder what good it does if it doesn't even amplify. In fact, the value of this circuit is not in amplifying, but in bridging. Almost no current flows into an op-amp's input, and its output can supply plenty of current. Thanks to this property, it can pass a voltage on to the next circuit without burdening the previous one. Placed in between, it keeps the two from interfering with each other, a buffer so to speak. It's understated, but it's a very useful technique, so keep it in the back of your mind. Next is the summing circuit, an application of the inverting amplifier. This is a circuit that gathers several inputs into the minus input, each through its own resistor. As we saw earlier, the minus input is held at a virtual ground that is nearly 0 volts. Thanks to this, each input can be added together cleanly without interfering with the others. A familiar example is an audio mixer. This summing circuit is what's used when combining the sound of several microphones or instruments into one. One thing to state precisely, if the resistor values differ, the weighting in the sum changes. Only when the input resistors and the feedback resistor are all the same value do you get a simple direction-flipped addition. Conversely, by changing the resistors, you can also mix while adjusting the volume. We've seen several circuits, so let's organize how to choose between them. The non-inverting amplifier suits cases where you don't want to burden the previous circuit, or where you want to keep the signal's direction as is. The inverting amplifier is used when you want to combine several signals like the summing we just saw, or when you deliberately want to flip the direction. And the voltage follower, with its gain of 1, is used to bridge circuits together. For amplifying microphone and sensor signals like we saw at the start, you'd choose a non-inverting amplifier if you want to keep the direction, or an inverting amplifier if you want to use the flip, picking these circuits to match your goal. And so today we've talked about the op-amp. An op-amp is a part that amplifies the difference between its two inputs by a very large amount, and because that's hard to use as is, we apply feedback to set the gain. And the biggest point today, when feedback is working and the output isn't railed, the plus and minus inputs sit at nearly the same voltage. Using that virtual short rule, the gains of the non-inverting amplifier, the inverting amplifier, and the summing circuit all become clear and simple. These are all basics, but once you have them down, circuits that use op-amps become much easier to read. Please keep them in the back of your mind.